Hi everyone, welcome to week 13 CE222 recitation. So let's get started with our first problem. The problem 12.4.2. A chemical industry need to make repair to its wastewater treatment plant, which is located near a river. A leaf is built to protect the construction work from the 10-year flood. So the question asks us, what is the probability that the construction site will be flooded in the 2-year construction period, and what is the probability that it will be flooded in the first and second year? So let's first decide what is the probability of the occurrence of this 10-year flood. So the probability, because it's 10-year flood, so it's just 1 over 10. And we can write it as 0.1. So that is the probability of the occurrence for this 10-year flood. And the first question is saying that what is the probability the construction site will be flooded in the 2-year construction period? So in other words, we can interpret these as the probability 1 minus that there's no flood for the consecutive 2 consecutive year. So we want to y minus the probability of this. And 0.1 is the probability for the flood to occur in a year. So the probability for no flood to occur is 1 minus 0.1. So this is equal to 0.9. That is the probability for a year that no flood occur. So we want to calculate the probability for 2 consecutive years. And to do that, we can just square this 0.9. So the entire term will become y minus 0.9 to the power of 2 because it's 2 consecutive years. And this will give us the answer 0.19. That is 90%. And the second problem asks us, what is the probability that it will be flooded in the first and second year? So that's also very straightforward. You have the flood, the probability occur in the first year is 0.1, as we said here. And the probability for the flood to occur in the second year is also 0.1. And you want them both to happen, so it's basically just times these two number up. And this gives us 0.01. That is 1%. Okay. Okay, let's look at the next problem. Problem 12.4.3. A city depends on the well field for its water supply. If the well's yield during the dry season drops below a base level of 8,600 CFAs, various emergency action begin. After 2 consecutive years of sub-base flow, a small reservoir is brought online. And after 10 consecutive days of the sub-base flow, water must be piped in from a nearby city. And they tell us the existence probability for 2 days drought is 40% and the 10-day drought is 10%. And here we are more interested in the 10-day drought because this is the threshold that you have to pipe the water from. You have to pipe in the water from a nearby city. Okay, so let's start to answer the question. In the first sub-question A, it asks the probability of having to pipe in water at least once in the next 2 years. So follow the similar concept from the previous problem. It's 1 minus that we don't have to pipe in the water in a year. So it's 1 minus this 10%, which is 0.1, 0.1. This is the probability that you don't need to pipe in the water in a year, and we want to do this for at least 2 years, so we need to square it. Therefore, we got a probability for this A problem as 19%. 0.19 to 19%. Okay. And for the problem B, we want to calculate the probability of not having to pipe in the water in the next 2 years. Okay, so that is also very easy because you don't want to pipe in water, so that means we want to calculate the probability of 1 minus 0.1. That is the probability that you don't have to pipe in the water in a year, and now we want to do it for the next 2 years, so we need to square it. This gave us 0.9 square, which is equal to 0.81. That is 81%. Okay, and for the problem C, we want to calculate the probability of having to pipe in water during each of the next 2 years. So, the probability of a year that you need to pipe in the water is 0.1, and you want to do it for the next 2 years, so you just square it. Then you got 0.01, which is equal to 1%. For the problem D, we want to calculate the probability of having to pipe in water exactly once in the next 2 years. So we have 2 different combinations. One is you pipe in the water in the first year and don't pipe in the water in the next year. Or the second, this is the first one. The second one is you didn't pipe in the water. You didn't need to pipe in the water in the first year, but you have to pipe in water in the second year. And so you just need to sum these 2 probabilities up to give the overall probability of having to pipe in the water exactly once in next 2 years. So to do that, for the first combination is 0.1 times 0.9. So 0.9 is that you will have this drought occur. The probability of this 10-day drought occur that you have to pipe in water. And 0.9 is 1 minus 0.1. So this is the probability that you don't need to pipe in water because there's no 10-day drought occur. Okay, so similarly for the second combination, you just switch the order, which is 0.9 times 0.1, and you sum these 2 up, and you will get 0.32, which is 32%. Okay. Let's go to the next problem, the problem 11.2.13. In this problem, we want to determine the SCS 10-year 24-hour storm hydrograph for Miami, Florida for the time period from 9 to 13 hours. Also, we want to determine the peak intensity for the storm. So, to determine the height graph at this location, we need to first identify the overall rainfall for this 10-year 24-hour storm. Second things, we want to translate the overall rainfall into a height graph, and we will use the SCS curve, which we need to determine which type of rainfall distribution that we should use. Okay, so Miami is located at somewhere here. So this, from the figure 11.5, we know that the overall rainfall for the 10-year 24-hour storm is 9 inch, and this is for Miami. The second thing is we want to determine which rainfall distribution type we should use. So similarly, Miami is somewhere here. So this tells us we should use the type 3 rainfall distribution. So that's the second information that we need. Type 3. Okay, then we can move on to this figure 11.8. And now we want to convert this 9-inch rainfall into the rainfall distribution. Okay, that's the things we want to do in the next step. And we want to use this SCS curve for the rainfall distribution. And as you see, this figure is so-called the CDF function, so it's accumulated function. And what we want to find is the peak intensity. So that means what we really need is PDF. So to convert a CDF to PDF, we want to translate this curve into a form like this. So we can find out the peak intensity at the highest point. To do that, we use a discrete method to do this translation. So to do that, let's use the delta t equal to 0.5 hour as a resolution to discretize this CDF function that's shown in the figure 11.8. So, in a way of speaking, we want to calculate the difference. For example, this is 16, right? And we want to calculate the difference between 16 hour and 16.5. So we calculate the difference here, and we can translate into the height. And if you calculate the difference over this time horizon, then you can get the difference for each interval, for each half hour interval. Then you can get a distribution, something look like this. Then you can identify the peak intensity using this discretized PDF. Okay, so I will use this concept to do the following calculation. Okay, let me erase this first. And let's look at the problem again. So the problem only tells us to calculate between 9 to 13 hours. So that's write down the solution in this table. We first use the half hour interval to discretize the time step between 9 and 13. And we want to calculate the difference, so we have a second column showing a shift of 30 minutes, which is 0.5 hours. Then we use the figure in use the figure in 11.8 to identify corresponding value for the fraction of the 24-hour rainfall. So for example, for the column 3, we use the first column time step. So 9 hours, and we just say that Miami is located in the type 3 region. So we just draw a line here, and it's approximately about 0.148. And similar things we can do for the second column, 9.5 time step, to calculate the column 4. So this is 3. So 9.5 is somewhere here. And we can read it's slightly higher here. I know it's not really accurate. If you want to find an accurate value, you can actually go online and search SCS 24-hour rainfall distribution, and you can download from the internet, and you will get the spreadsheet for the accurate number. But here we just approximate the number by reading this graph. So here I will tell you it's about 0.187. Okay, so after we got this is the fraction of the distribution, right? So next we want to calculate the actual rainfall amount, and we know that the total rainfall amount is 9 inch. So to calculate the rainfall amount in this particular time step, you just times 9 to the 3 and 4 column, and you will get the column 5 and column 6, which is 1.32 inch at the 9-hour time step, and 1.503 for the 9.5 time step. And next we want to calculate the difference, right? As I showed before, we want to build this discretized PDF. So you calculate the difference between column 5 and column 4, column 5 and column 6, and you will get the number 0.171. Okay, so this is the amount of the rainfall that will fall between 9 hour and 9.5 hour. Then to convert this back to the intensity, we note that this amount of rainfall is happening in half hour. So to convert it into the units of inch per hour, you just do this. Delta, let me write the formula first. So this column 8 will have the formula delta P divided by 0.5 hour. Okay, and you just plug in the number here, 0.171 divided by 0.5, which is 0.342. And you just following this step for each row, then you can obtain this table here. Then this column 8 is the distribution, is the Haito graph that you need to calculate for this problem. And to identify the peak intensity, you just find the largest value in the last column, which is 5.436 inch per hour is the peak intensity in this rainfall event. Okay, so you finish this problem. The key is just to that you need to know is to use these two figures to identify the basic information for this 10-year 24-hour stone, and then you use this SCS curve to calculate the height of graph using this CDF to PDF calculation process that I just described. Okay, let's look at the last problem for this week. So now we have a rainfall event shown in this table, and the problem asks us to determine first the total depth of rainfall for this 10-hectare urban watershed, and second, we want to determine the maximum intensity. And the last information we need to calculate is the total rainfall volume. Okay, let's do this one by one. To determine the total depth of the rainfall from this table, is basically you just sum this up. Okay, so you just sum the rainfall depth for each time interval up. Okay, rainfall depth and this gives us 3.81 centimeter. For the problem 2, we want to calculate the maximum intensity, so we can calculate the intensity for each interval. And the intensity's formulation is delta P, which is the rainfall in that certain interval divided by the length of that interval, delta T. Okay. So the delta here is 6 minutes. This is 12 minutes. This is 3 minutes, 9 minutes, 6 minutes, and 10 minutes. Oh, no, 9 minutes, sorry. And by just looking at this volume, I mean, you can calculate the intensity for each interval and select the largest one. But here, to save the time, I will just tell you the largest intensity is happened at this interval, which you somehow can guess it from the value you got here. But let's just calculate the intensity for this interval for demonstration. So we know that the delta P is 0.46 cn here, and we want to divide by the time interval here, and we want to express it in the units of hour. So 3 minutes divided by 60 is, you just convert the unit from minute to hour. So this is hour now, and then you can get the intensity is equal to 9.2 cn per hour. Okay, you should double check this answer is the maximum intensity by calculating this intensity value for each interval here. Okay, but I will leave that work to you. So for the third problem, we want to calculate total rainfall volume. So that is also straightforward. You just need to times the depth to the area of this region. So the total rainfall depth is 3.81 centimeter as we calculate in the first sub problem. And we want to express them in the units of meter, so it's 0.0381 meter. And then we want to times the area to calculate the volume. So it tells us that the area is 10 hectare. So that's times 10, and 1 hectare is equal to 10,000 square meter. So we need to times this 10,000 for the unit conversion. Then we will get that the volume is 3,810 cubic meter. Okay, then we finish this problem. See you next week.